Alright, here in this video I'm going to start talking to you about epoxide ring openings. I think epoxide ring openings are really cool. Some students really struggle with it, so I'm going to try to be really clear about what you need to look for in order to figure out how to open an epoxide ring. So the biggest key that you need to keep in mind for epoxide ring openings is that you have to watch the conditions. There are two sort of different conditions that epoxides can react under, and depending on which kind of condition it's under, it will open differently. So be sure that you watch the conditions. Just like we look at the conditions to determine SN1 versus SN2, we're going to watch the conditions here to figure out exactly how the epoxide is going to open. So the first set of conditions is with strong nucleophiles. Strong nucleophiles are like alkoxides. So methoxide here, that's a strong nucleophile. You know it's a strong nucleophile because it's negatively charged. So that would be favoring SN2 type conditions, strong nucleophile. Hydroxide, it's a strong base. We've used this to do elimination reactions. It's also a strong nucleophile, again, because it's negatively charged. You can open epoxides also with sulfides or, negatively charged sulfur atoms. That's a strong nucleophile because it's negatively charged. So strong nucleophiles favor this first kind of ring opening I'm going to talk about. This kind of ring opening is SN2-like. It's not completely SN2, you'll see, but it's very similar to a typical SN2 reaction. The key, though, is a backside attack occurs. So we have to watch the stereochemistry. The nucleophile will come in from the backside, causing inversion of a stereocenter. And just like an SN2 reaction, it's going to go to the less hindered side of the epoxide because the transition state would be too crowded if it came in on the more hindered side. So all of this is consistent with an SN2 reaction. So let's talk about an epoxide. So here is an epoxide, and this epoxide I'm drawing right now is achiral. Because you can see there are two methyl groups at this, but I'm trying to draw it one. That's not what I wanted to draw at all. Hold on a second. There we go. There we go. Now it makes sense. So these three atoms of the epoxide are in the plane. This methyl group is coming out of the page at you. This methyl group is going away. It's achiral because this carbon center has two of the same groups coming off of it. So it is an achiral epoxide. Over here, we have a hydrogen coming forward and a hydrogen going back. We're going to react this epoxide with a strong nucleophile. I'm going to react it with methoxide. So if we look and see here, it doesn't really look like we have any good leaving groups, but epoxides are particularly strained. So if we were in class, I would ask you, what is the hybridization of this carbon center? And you'd tell me that it was sp3. I'd ask you, what is the geometry at this carbon center? You'd tell me tetrahedral. And I would ask you what the bond angle is. You'd tell me 109.5. That's the ideal bond angle for a tetrahedral center. But because this ring is constrained down to 60 degrees, it really is strained. It really wants to pop open. That willingness of the epoxide to pop open to get back to an ideal bond angle is the reason that these things actually do react with nucleophiles. So we're under basic sort of conditions, strong nucleophilic conditions. We're going to have the reaction occur at the less hindered side of the epoxide, and it's going to come in from the back side, pushing the epoxide open. So this is the most important thing when you're drawing these reactions of epoxide. I really want you to focus on this anti-geometry. So here's the O that's opening up. It's actually going to be an O- because the electrons that were in this bond are now localized on the oxygen. And this nucleophile that comes in is anti to the oxygen ring that was part of the ring because it comes in from the backside. So it opens from the backside and the oxygen is then in the anti position. So this is really crucial. And if I were doing this on the board at school, you would see me, I always draw this first before I figure out what's happening at the other sides. So now I look and see what I've got over here at this carbon center. At this carbon center, again, it's achiral. I'm just going to draw it. One methyl group is coming forward, one methyl group is going away. Now, we typically are going to finish this reaction. A lot of times this reaction is also done in water or something like that. Assume that you can find a proton around to react with. In this case, the proton or the base, that oxygen minus, that alkoxide, will just get protonated from a proton that's around. So just assume that you can find a proton if you need one. So this is the oxygen that was part of the epoxide ring. This OCH3 was the nucleophile that came in, and this is in the anti-configuration. Let me do another one that actually has some stereochemistry so we can see it. So let me just get a blank slide in here so we can show you what I'm talking about there. So again, this is epoxide ring openings under basic conditions. So now let's look at an epoxide that has some stereochemistry. So here we have a cyclohexane ring, and the epoxide is coming off of the cyclohexane ring, and it's coming out at us. So all of the cyclohexane rings are in the plane, and then the O is coming out at us as part of the epoxide. Epoxide three-membered ring, where one of the members is an O. We're going to react this. The first part of the reaction is going to be with sodium. I'm going to use methoxide again. And then the second step of the reaction is going to react with water. Okay, so this is where we're going to analyze to see. I'm going to bias this system. I really want to make that a little bit more tricky so we can really have this make sense. So I put a methyl group there. Okay, so we analyze the conditions. We're under strong nucleophilic conditions. Strong nucleophilic conditions are SN2-like. SN2-like means that the reaction is going to occur at the less hindered side. This side, you can see it's tertiary. This side is secondary. An SN2 reaction is going to occur on a secondary carbon significantly faster than it would ever occur on a tertiary carbon. So this strong nucleophile is going to come in from the back side and push that oxygen away from it. So the products of the reaction look like this. This oxygen, this bond here, never got broken. This bond here didn't get broken during the course of the reaction. So this stereocenter doesn't change. We still have a methyl group going back, and we have the O- group that's coming there. This is the bond that broke, right? This is the broken bond. The yellow bond stayed the same. The turquoise bond is the one that broke. This OCH3 had to come in from behind. From behind means the OCH3 takes up that position. So now that's what occurs in the first step. In the second step, we react it with water. Just like I showed you in the other reaction, water is there to protonate our alkoxide intermediate. I'll just draw this down here. So the overall product of the reaction is an alcohol and an ether in an anti-arrangement to each other. So the alcohol is coming forward, the ether is going back. That's anti to each other because the nucleophile had to come in from behind. So again, under strong nucleophilic conditions, strong nucleophile, that will take place at the less hindered side, and it will take place with inversion. The nucleophile has to come in from the backside. Now we're going to get a little more complicated because, oh, that's just a summary slide there. Now we're going to get complicated. What happens if we're not under strong nucleophilic conditions, but rather we're under acidic conditions? Let's take a look. Again, I'm going to make this really straightforward at first, and then we'll get more complicated. So here is an epoxide, and we're going to see what happens and what the difference is when we react this epoxide under acid. Hopefully by now, you guys are used to this. Oxygen sees acid, gets protonated. All right, so let's analyze this protonated epoxide. That oxygen does not want to be positively charged. The reason that oxygen doesn't want to be positively charged is because it's an electronegative atom. So what atom in this protonated epoxide would rather be positively charged? One of the carbon atoms. Carbon is less electronegative than oxygen, and so it can handle the positive charge a little bit better. So this protonated epoxide, I'm going to draw it like this because that's really what's happening. But you can think about it, and this is the only time I use dashed bonds, because you guys should know by now I hate dashed bonds. You can kind of think about it like this. It would rather have the positive charge be on the carbon atom than on the oxygen. So if we were to break this bond here, let me highlight that so you see. If we were to break this bond, that would put the positive charge on that carbon atom. And that's a little bit better than having the positive charge on the oxygen atom. So this is going to come into play when I actually put some substituents on there. But this is one way that you can think about it. Now what happens? Pretty straightforward. SN2 type reaction. This comes in from behind. I think that's going to erase in a second. Yep. This comes in from the back side and opens the ring up. So you have the stereochemical implication of anti. So again, I'm going to really emphasize the fact we broke this bond. The chloride came in from behind. The alcohol and the halogen are anti to each other. We don't have any other substituents on this, so we just have hydrogens at this carbon and hydrogens at this carbon. But again, we have the anti relationship between the two of them. So, under acidic conditions, there's kind of a mix of SN1 and SN2 properties. The reaction is going to occur at the more hindered side, because the more hindered side is going to be able to handle the positive charge better. But it will still occur via backside attack because there's no true carbocation here. That bond is kind of like it's broken, but it's not. It's not broken. So the nucleophile is still going to come in from the backside. So let's put some actual substituents and stuff. That's going to go away in a second. There we go. Okay, I'm going to still give you an achiral molecule. So this carbon has two carbons coming off of it. This carbon just has hydrogens. And we will, once again, we'll react it under let's do hydrobromic. Okay, so the first step in this mechanism, oxygen sees acid and gets protonated. All right, so now we have to analyze and see, well, where is this reaction going to happen? This epoxide ring wants to open so bad. Like now we've protonated it, it wants to be open. So we look to see, we have this positive charge. Which side of the epoxide is going to handle the positive charge better? And it's this side here, because that, again, if I draw the terrible dashed bond thing that I don't like, you'll see that that side is tertiary. That's going to be able to handle the positive charge better because we have the friendly neighbors that are donating electron density in. So in this way, still from the back side, the bromide comes in and opens the epoxide. The product that's formed, again, focus on the anti relationship between the nucleophile that came in and the alcohol group. Then we also have the two carbons coming off of there. I'm going to do one more example on a ring so you guys can see that even better. But before I move on, I want to say, what did we form? what kind of functional groups are present in this molecule. So if we were in class, someone would be like, oh, there's an alcohol. And then someone else would be like, oh, there's a halogen. And I would say, well, what are those? That is a halohydrin. And we've talked about halohydrins before. We know that we can react halohydrins with strong bases. Strong bases then would form the epoxide. So we can go back and forth between an epoxide and a halohydrin. So that's going to be important for later on when we actually do synthesis reactions. All right, next up, I'm going to show you another one under these acidic conditions, and I'm going to do the same ring that we did previously, so we can get some of that stereochemistry issues in there as well. So we're going to react this with hydrochloric acid. Okay, so first step, alcohol sees acid and gets protonated. Again, I'm really hoping that that's second nature by now. Protonation makes the epoxide ring want to open even faster. So it already wants to open because it's strained. It now also wants to open because now it's got the positive charge. So figure out which side the nucleophile is going to come in on. It's going to come in on this side because it's more hindered and there's more carbons there. So this positive charge is more stabilized here. Again, I'm going to draw this terrible dashed line bond thing. I really hate it because I don't really get what it's trying to show you. But the positive charge is more likely to be there than it is to be over here. This is tertiary versus secondary. So now the chloride is going to come in from behind to open up the epoxide ring. So focus on that anti-relationship. It had to come in from the back. So the chloride is behind. The alcohol is up. We didn't change this bond, okay? This is the bond that stayed the same, so it stays the same. This is the bond that was broken. It's broken, it goes behind. So where did this methyl group go? This methyl group got pushed up as well. So the anti-configuration between the alcohol and the halide, and then that methyl group stays coming up. All right, let's do another example. Let me bias the system here, make it, you know, at least somewhat interesting. There we go. And then let's react this with sodium hydroxide in the first step, and then in another step we'll react it with water. Okay, analyze your conditions. We're under strong nucleophilic conditions. Strong nucleophile because the hydroxide is negatively charged. Strong negatively, oh, I have to give you some stereochemistry here as well. Oh no, that's going to go away. I guess we'll make this coming out at us. That's the hydrogen. And we'll make the methyl group anyway. So just so we're really clear, we have a methyl group here and we have a methyl group here. Okay. So, strongly nucleophilic conditions. Strong nucleophilic conditions, SN2. We're not protonating this, so we don't have to worry about any carbocations or positive charges. This is straight SN2. This side of the epoxide is tertiary. This side of the epoxide is secondary. So this is going to come over here and push that away. And again, I really am going to focus on the anti-relationship between the alkoxide that we formed from the ring open and the nucleophile that came in. Those are anti to each other. So now this hydroxide that's coming from the back is going to push that methyl group up. Hold on a second, let me think about that for a second. Yep. I recommend you build a model if you can't see this happening. that methyl group is going to get pushed up. We've inverted the stereochemistry because now our hydroxide, our group number 1, highest priority, is coming down, whereas here our highest priority group is coming up. That's how the stereochemistry is inverted. This stereocenter hasn't been touched. So we still have the ethyl group coming forward, and we still have the methyl group going away. All right, let's do the same one under acidic conditions. Sure, why not? So let me just redraw this epoxide, and I'll redraw in the stereochemistry. Let's react it under, let's do sulfuric acid conditions. Oh, I'm sorry, I didn't finish this reaction. The end of this reaction, the alcohol, the alkoxide is going to get protonated, so we would form a diol, an alcohol here and an alcohol here. Let's do this under sulfuric acid conditions. Sulfuric acid conditions, the epoxide sees the alcohol and gets protonated. Now we look around and find the best nucleophile that's going to end up reacting with this. The best nucleophile is the water. Remember, the conjugate base of sulfuric acid is non-nucleophilic. This has a positive charge. So which side is going to be attacked by the nucleophile? This right-hand side, because that's going to be tertiary. So this is going to attack the more hindered side, but still from the back side. Focus on the anti-relationship between the alcohol that was part of the epoxide and the water. This one, the stereochemistry gets inverted simply because we're switching the positions. Priority group is up, priority group is down. That changes the stereochemistry. This stereocenter hasn't been touched. So we still have the hydrogen coming forward and the methyl group going away. And again, finishing this reaction, water would come to deprotonate this, and we would form a diol.